This lesson is about variable data control charts, specifically about one type of variable data control chart. Before we get to that particular kind of chart, generally speaking, when we think about variable control charts, we are talking about measurement data, something that can be measured. So we're talking about characteristics of a product or a process, such as the weight of a product, the height, the length, the viscosity of a particular liquid, the density, those kinds of things. So it's something that can be measured. To put it in simpler terms, it's where decimal points have a meaning. So if we talk about 22.8 degrees or we talk about 34.8 inches, it has meaning, rather than when you're talking about discrete distributions where there are no decimal points. So we're talking about continuous distributions here, right? We're talking about measurement data. The difference between attribute control charts and variable control charts is that variable control charts they are used in pairs. So you're always looking at the variability in some kind of a measurement of range or measurement of standard deviation, in addition to looking at the variation in the mean. So they're always going to be in pairs. So that's why we call this the X bar R chart that we're going to look at next. We don't use the X bar chart without the R chart or the R chart without the X bar chart. They always go in pairs. They study process averages and they study the process variability. And that variability can be measured. In our case, we'll be looking at range. It can be measured as standard deviation. So there may be different types of control charts using different aspects of variability that they're measuring. Now, let's take an example here and work through it to get a sense of the X bar R chart. So we have Holly, who is a barista at a coffee house, and she is known for her the cold Americanos that she sells. These are white Americanos. These are with cream and milk in them, and she prides herself on making these, right? She builds each drink with a very elaborate process that involves making the espresso in stainless steel cups that have been pre-cooled, transferring them into a glass cup, adding the cold milk, which is maintained in a refrigerator at a certain temperature, set at 34 degrees Fahrenheit, 0 degrees Celsius. Right. Now, Holly wants to assess the consistency of temperature that she gets from making these Americanos. So she wants to see whether this works out to be within a certain range. So she wants to see how good this is in terms of the variability that is in the process. So what she has done is she has collected data over the last 5 days using samples of the first 4 Americanos. So each of those 5 days, she's taken the first 4 Americanos that were made between the 12 noon to 1 p.m. hour each day. So what you have on this slide is the data that she has. So in the rows, we have each of those samples. So that's day 1, day 2, day 3, day 4, day 5. And then what you have is in terms of the temperature for each Americano, 4 Americanos that are taken on each of those 5 days. So what is the sample size here? The sample size is 4, and the number of samples that she has taken is 5 samples of size 4. This is going to have some meaning when we do some calculations, so it's worthwhile for you to make a note of that there are 5 samples of size 4. Right, so let's get into some basic calculations of this. So what can we see in terms of the basic averages and the ranges that we can get from this? So we're moving towards a X bar R chart, a mean and range chart. So the first thing that we need to do is take each sample, take each row and calculate its average. You add them up, you divide by 4, you get an average, right? And then for the range for each of those rows, you want to calculate, take the maximum, subtract from that the minimum, and you get a range. So if you do that for all 5 samples, you can get the ranges and the averages for all samples. And what you have in the last row is the average of averages. So it's a mean of means. So the 35.08 is representing the mean of means for all of the samples. And then you have a range average of 0.074, right? So that's what we get from simply looking at the averages and the ranges. And what you're also seeing over here is these averages are going to be used as the center lines for both of those charts. So you've already got the center line for the range chart as well as the average chart. All right, now let's look at the computations for the upper and lower control limits. Now, if you're not comfortable with symbols, with Greek symbols, you might be intimidated by these, but what these are basically saying is that the upper control limit for the range control chart is going to be based on the average range that you've already got. So what you're looking at, sigma r divided by k, is simply the average of all the ranges. So you take the average range and you multiply with something called the D4. The lower control limit for the range chart is based on a D3 number, multiply that with the average range. And then when you look at the upper and lower control limit formulas for the means chart, you're looking at the mean of means, and that's why you have the double bar on top of the x. It's saying that it's the average of the 5 averages that you had taken plus the A2 times R bar. Lower control limit is x double bar minus A2 times R bar. Now, the question that you should be asking or what you should be wondering about at this point is, what is this D3, D4, and A2? What are these things and where did they come from? So where they come from is this chart that we can use to pick out these values. So what is this chart? This chart is taking the different sample sizes that you might use and giving you the different A2, D3, and D4 values that you would plug into those formulas. Now, where are the numbers coming from? They're basically representing the idea of 3 standard deviations. So because we have a very small sample size, it's not appropriate for us to use standard deviations. We are using the idea of 3 standard deviations by substituting with these multipliers. So the A2, D3, and D4 are multipliers that help us replicate the idea of plus or minus 3 standard deviations. So the one that is going to be the one that we are going to use here is based on our sample size of, now you may recall that I said earlier we have 5 samples of size 4. So we go to the row that says sample size of 4, and it tells us 0.729 is the A2 value that we need to use, and then 0 and 2.282 are the D3 and D4 values. So we're simply going to take these and plug it into the formulas. The center line for the range chart is based on the mean of the ranges. We already got that earlier as 0.074 from that table that we had. The upper control limit is going to take that 0.074 multiplied by the 2.282 multiplier that you saw on the chart on the previous slide. So upper control limit is 0.1689. Lower control limit based on a multiplier of 0 is going to be 0. Right? So we get the upper and lower control limits for the R chart. Similar calculations for the X chart, the X bar chart. Center line is based on mean of means. Upper control limit is mean of means plus the multiplier 0.73. The multiplier in this case is the A2 value. And for the lower control limit, you're using the same multiplier, but you're subtracting in this case. So you have mean minus 0.73 times the range. Now, what you've noticed over here, or what you should have noticed over here, is that between these two charts, between the range chart and the X chart, in the X bar chart, between the R bar chart and the X bar chart, we are using the range to come up with the upper and lower control limits for the X bar chart, right? So this seems kind of strange that we're using something from a different chart to compute the upper and lower control limits. But why the reason I bring this up is because it's important for the range to be in statistical control if you are going to use that range to compute the X chart. In other words, you need both of them to be in statistical control to call a process as being in statistical control, or to come up with the inherent capability of the process. You need both of them to be within the statistical control limits, right? All right, so let's take a look at the interpretations of the chart by plotting the points on each of these charts. So once again, like you had earlier for the other kinds of charts, here for the X bar R chart, you have the points plotted on that chart of upper and lower control limits. What do you see here? You see a nice level of consistency. Right now, once again, we've used, as we talked about in the case of the proportion chart and the count chart that we looked at earlier, we've used a very small number of samples to come up with these values. So if you were to do this problem in reality, you would want to get a larger sample and use that. What I'm talking about is the number of samples. Your sample size may remain small, but you definitely want a larger number of samples to come up with a upper and lower control limit. 5 samples is not going to be enough. All right, so taking these results for what they are, let's take a look at what this implies. What this is showing us that Holly's process is pretty consistent, right? She's giving a pretty consistent temperature. The maximum that it varies is 0.1688 degrees Fahrenheit. The maximum of that range chart was a 0.1688 degrees Fahrenheit, which is pretty good. The range is pretty small. It's between 0 and 0.1688, right? The temperatures for the actual icy cold Milky Americanos is between 35.0356 and 35.1434 degrees Fahrenheit. So again, a very small range of temperatures that you're getting from this. So it seems to be a pretty tightly controlled process. She's able to achieve that consistency in the coffee that she's serving her customers. Now, the question that you have not addressed by looking at whether the process is in statistical process control and even focusing on the inherent capability of the process is, what is the customer's expectation, right? We don't know how this temperature compares to what the customer expects, whether the customer is going to be happy with this particular temperature or not. That's something that you don't know from doing a statistical process control analysis. So keep a note of that.